Okay, good evening, everyone. Welcome to 8th class of Deterministic Network Calculus. So, small recap. So, last class we saw about some properties of Kleene star operator. So, given a complete dioid and the binary operators plus and minus, the Kleene star operator was defined as so for A belongs to T. A star was the Kleene star operator, which was defined as plus I equal to 0 to infinity AI, where AI equal to A into A and A0 was the unit element. Yeah. Uh, Next, we also saw the theorem that for the affine equation, A uh, for the affine equation x equal to A into x plus b, uh, the least solution was A star b or A star into b, right? So let me give an example. So we'll have an example today. So let me think of an example. So example is, so let us take the total dioid, so the complete dioid. R plus R min plus and min operator and addition operator. So this is a complete dioid. So uh, now let A comma B belong to R min plus, right? So we have x equal to A into x plus B. Now our claim is x equal to A star, right? So A star is defined as in I equal to 0 to plus infinity AI, right? A0. Here, for this total line, the unit operator E is 0, right? If you add anything to 0, it will become 0. So A0 equal to 0. A1 equal to A plus 0 equal to A2 equal to A plus A equal to A and so on. So A star equal to min of 0, A, 2A and so on, which is 0, right? Next, we have A star into B, which is 0 plus B, which is B. Therefore, the claim is that the least solution to the affine equation x equal to A star B is x equal to B because A star B equal to B. So now let's substitute B in place of x in this equation and see is it true. So we have min of A, sorry, we have um, min of x equal b equal to min of a plus b comma b, which is b. So b equal to b, hence x star a star b is a solution to the affine equation x equal to ax plus b. Okay, so here was an example for the future node. Next, we saw something known as subadditive functions. So what was subadditive function? So f of x plus y is less than or equal to f of x plus f of y. Then it is known as subadditive functions. Some examples of subadditive functions were constant function, affine function of the form rho t plus sigma, where sigma is greater than or equal to 0. This is not the diode order, this is the normal order. Okay, next we have ceiling functions. We saw that subadditive property is closed under addition and convolution, but is not closed under minimum. We saw an example for this in the last class. Okay. Next we saw these properties of subadditive function. Next we define subadditive closure operator. So subadditive closure operator okay, so now we have taken the complete diode, the set of min plus functions, pointwise minimum operator, and convolution operator. So this is a complete diode, right? Now, if you have a function f belongs to the the min plus functions, then f star, the Kleene star operator, is defined as min of I equal to 0 to plus infinity fi, where f0 equal to e. Now, the unit function of this diode is so e of t equal to 0 if t equal to 0, plus infinity if t is greater than 0. This function is the unit function. So if you do convolution, if you perform convolution with any e of t, you will get the function back. If you perform convolution with any function with e of t, then you'll get that function back. This is the unit function. And fi is f convolution, fi plus 1 is f convolution f, right? So we know that the pointwise minimum and addition have the distributivity and associativity property, right? So basically your f and t is infimum set of summation I equal to 1 to n f of ui, such that ui, u2, so on to un belongs to R plus, and summation of I equal to 1 to n ui equal to t. Okay, so let's write this out first. So let's first write f1 of t. This is equal to e convolution with f, which is inf 0 less than equal to s less than equal to t E of S plus F of T minus S. Right, now you will see that this low latent infimum at S equal to 0. So this is equal to F of T. Similarly, F2 of T is basically F of T convolution with F of T. So this F convolution with F at the point T. Okay. So this is basically inf 0 less than equal to S less than equal to T, F of T plus F of T minus S. Or you can write this as inf U plus V equal to T. This is S. And set of FU plus FV. Right? Now, if I have F3 of T, it is basically F2 of F2 convolution with F at T. Right? So you have inf V plus, okay, let's do one thing. Let's make this more simple. Let's do this as we have defined. So this will become U1 plus U2. This is U1. This is U2. And next we'll write yes U3 plus U1 plus U2 equal to T such that F of okay U3 plus U2 prime equal to T, U3 plus infimum of U1 plus U2 equal to U2 prime, F of U1 plus F of U2. Right? Now I can bring this in from outside. Inf U3 plus U2 prime is U1 plus U2. I'll replace here U1 plus U2 equal to T. And inf 2 times you'll get the same result. It will be U3, U1 plus U2. And as you can see, the pattern emerge here. So F and T is basically inf over summation I equal to 1 to n FUI such that this summation I equal to 1 to n UI equal to T. Okay. And similarly, F star T. Right. This is infimum over all n's. And your infimum summation I equal to 1 to n FUI such that summation I equal to 1 to n UI equal to T. This happens. So this is there is an infimum object. So this infimum is basically this operator, right? And the whole inside part is basically this operator. This is basically this. Okay. So this is the subarrative closure operator. Okay. Yeah. Next. So we'll give an example of the subarrative closure operator. So let's take a function f of t such that it is 1 if t is greater than or equal to 1 and plus infinity if t is If t is less than or equal to 1, and t is greater than 1, and ends plus infinity. So basically the function looks like this. So the f function looks like this. This is 1. And this is 1. Okay. So now we'll calculate f2 of t. So f1 of t is f of t. This is basically inf summation I equal to, this is f1 u1 plus f2 u2 such that u1 plus u2 equal to t. Now, if t is less than, okay, so case 1, if u1 plus u2 is less than 1, right? Sorry, if u1 is less than 1 and u2 is less than 1, then u1 plus u2 is less than or equal to 2, right? Then f1 u1 plus f2 u2 is equal to 2, because the maximum value this can get in the interval is 1 and the maximum value this can get is 1. So yeah, so under these conditions, so this implies if t is less than or equal to 2, then f1 plus f1 u1 plus f2 u2 is 2. So this will become f2 would be, so this is 2, this is 2, it will be 2 till 2, but then it will go to infinity. Similarly, if you take f3, f3 would be 3 till 3, that will, you need to take the minimum of all of this. So minimum of all of this would give you the lower closure. So this red line is the Kleene star operator on F or the subjective closure of F, right? These all other colored things are F2. This is F3. This is F4. Okay. So now we'll see some properties of subjective closures and also subjective functions. Okay. So theorem. If F is subadditive, such that f of 0 is less than 0, then f of 0 equal to minus infinity for all t greater than 0. And ft belongs to, then f0 equal to minus infinity, and for all t greater than 0, ft belongs to minus infinity or plus infinity. Okay. So proof. So let f0 less than 0. Right. Then f0 plus 0 is less than or equal to f0 plus f0. So since this can't be 0, so you have, because if you have any positive number on as a f0, so if you take f0 as 2, then 2 plus 2 is less than or equal to, sorry, if you have any negative number, because the condition is f0 is negative, f0 is negative, right? So if you take f0 to be negative, any negative number, so minus 2, this will be -2 less than -4, which is wrong. So for this to satisfy, okay, here let me make one more thing clear that these orders are all the natural order, not the diode orders. Natural order, not the diode order. This is also a natural order, not diode order. Okay. So the only solution that this equation can take is -infinity. Therefore, f of 0 equal to -infinity. Because if you take any other negative value, the inequality won't be satisfied. Similarly, for all t greater than 0, ft you can write as ft plus 0, which is less than or equal to ft plus f0, right? So again, the solution would be -infinity, but it could also be +infinity because +infinity here, for as we have discussed in previous classes, +infinity will be taking as absorbing. So the solutions for this is ft is either -infinity or +infinity. Okay. Next in the theorem. For all f belongs to f, f star is subadditive. F star is less than or equal to f, and either f star of 0 is equal to 0 if f0 is greater than 0, or f star 0 equal to -infinity if f0 less than infinity. Okay. Next we have proof. Okay, so let's write what f star is, right? F star is f min, e min, I greater than or equal to 2, fi. I changed the order, so it will not matter. Now, from this you can see that f star is less than or equal to f because it is the min of two terms. Like it is either, so f star is less than f or this. So from this we got f star is less than or equal to f. That is this, right? Next we need to show subadditivity, right? To show subadditivity, first we'll calculate f n plus m s plus t. Right. So infimum summation I equal to 1 to n plus n fui such that u1 to un belongs to r plus summation I equal to 1 to n plus m ui equal to s plus t. That's what we have. Now this is less than or equal to inf summation I equal to 1 to n fui u1 to un summation I equal to 1 to n ui equal to s plus inf summation I equal to 1 to n f of ui condition on u1 to v1 to vm, this is m, such that summation I equal to 1 to m vi equal to t. Right. This we can write as fns plus fn. Now let's find f star s plus t, right? This is inf over n comma n, fn plus m, s plus t less than or equal to inf n comma n, fns plus fmt. This is from the derivation that we have done, that we have used here, fmt. This we have just used the Kleene star operator, definition of Kleene star operator. Okay, so now this is equal to f star s plus f star t. Then what we have shown is f star s plus t less than or equal to f star s plus f star t. Therefore, we have shown that the Kleene star operator is subadditive. Or you can say that this is the subadditive closure operator. We have shown that that is subadditive. Okay. Next, if f0 is less than 0, then f star 0 is less than 0, right? Because uh, f star is less than f. So if f is less than 0, then f star is also less than 0. Okay. And from lemma 1 of from theorem before from the first theorem, if any subadditive function the value of 0 is less than 0, then the value at 0 is equal to minus infinity. So we know that f star 0 is less than 0, and we also know that f star 0 is subadditive, so which implies f star 0 equal to minus infinity, right? Now, if f of 0 is greater than or equal to 0, then f I of 0 equal to I f of 0, which is greater than or equal to 0. Right? For this to happen, now f star of 0 equal to f of 0, which is e of 0, which is 0. Because these will keep on increasing, so you'll be stuck at the 0th part, so it will be 0. So if f0 is greater than or equal to 0, then f star of 0 is 0. If f of 0 is less than 0, then f star 0 is less than 0. Okay. So the next theorem, if f is subadditive, I will take a subadditive function, and you have f of 0 less than or equal to 0, then f equal to f star. Right. So we'll show that the Kleene subadditive closure operator on a subadditive function is the same function, right? It doesn't add more. So basically, when you're trying to perform a Kleene star operator on a subadditive, already subadditive function, it will be subadditive. It will be the same function. Okay, so proof. So we already showed that f greater than equal to f star in the previous theorem, right? And now we have the condition that f is subadditive. So what does this mean? It means that for all s comma t, s less than or equal to t, f of t less than or equal to f of. Okay, I'll let. That's the condition for subadditivity. f of t plus s is less than or equal to f of t plus f of s, and f of t is less than or equal to and you can also write f of t minus s less than or equal to f of t minus f of s. If f is subadditive, right? Give me 1 second. So uh, we have so we know that f is subadditive. Okay. So okay, let's take f convolution f, right? F convolution f will get inf 0 less than or equal to s less than or equal to t, get f of s plus f of t minus s, right? So this is equal to, and f convolution f is less than or equal to f of s plus f of t minus s. For any s, for all s less than t. Okay. Now, since f is subadditive, okay, keep this inside. Now, since f is subadditive, f of s plus t minus s is less than or equal to f of s plus f of t minus s, right? Therefore, f of t is less than or equal to f of s plus f of t minus s. Now, I just want to think things frozen. Yeah. So now, um, so we have seen that f star is less than f. No, no, no. Okay, so now take this, right? This is true for s equal to 0, right? So f convolution f at t is less than or equal to f of 0 plus f of t. Okay, from f is subjective, this is true for all s belongs to s greater than t, and that means f of t is less than or equal to inf 0 less than or equal to s less than or equal to t, f of s plus f of t minus s. So from this we get f of t less than or equal to f convolution f of t. Right. Now from this we use isotony of convolution, and we get f convolution f of t is less than or equal to f convolution ah of t. Similarly, this goes on both sides, and here you have f of t. This is all because the f is subadditive, right? We have used f is subadditive and we have got this. So we finally got ft is less than fi t. Okay. So we are given that f0 is less than or equal to 0. When f0 is less than or equal to 0, then f is less than or equal to e, because e is 0 at 0 and elsewhere it is plus infinity. So f will always be less than or equal to e, which is equal to f0, right? So we have f is less than or equal to, since f is less than all the fi's, f is less than e, f is less than f star, right? So from the previous theorem, so in the previous theorem we've shown that f is greater than f star. Now we are showing that f is less than f star if f is subadditive and f of 0 is less than 0. Therefore, f equal to f star. F equal to f star. That is what we want. So if f is subadditive, then the Kleene operator is also subadditive. Theorem. For all f belongs to f, f star is the largest subadditive function less than the function f such that f star 0 is less than or equal to 0. So what this means is, let there be a function g less than or equal to 0, and g0 is less than 0, and g is subadditive. And this implies g is less than f star. This comes from the previous two lemmas, right? Hence the name subadditive closure of f. So f star, that operator, it gives you the largest subadditive function that is less than the function that is given, such that f star 0 is less than 0. So let's do the proof here. So G belongs to a set of min plus functions. This is subadditive, right? That is given. This is subadditive such that G is less than F and G of 0 is less than or equal to 0, right? Then from isotony, we have that G star is less than F star. But since G0 is less than 0, this is equal to G, and hence G is less than or equal to F star. That is what we are showing here. Okay. So these are from the previous two games. There is one more theorem which gives the relation between minimum convolution and subadditive closure. That relation, I'll write it down. So F pointwise minimum with G and the clean star operator is F clean star operator convolution G clean star operator. Okay, so this relation I'll prove it tomorrow in the next class. So this will be used in computing subadditive closures of function. So yeah, the proof of this theorem we'll go in the next class. Further, I'll also introduce a deconvolution operator. This operator would be basically the inverse of convolution operator. Okay, we will define in the next class, we will do the proof for this theorem and also will define the deconvolution operator and see some properties of it. So that's it for today's class. Thank you for attending. We'll stop the recording.